Today we are going to be talking about Thevenin and Norton's theorems, or a better way to put it would be Thevenin and Norton equivalent circuits. And we are going to focus on finding the equivalent circuits for circuits that do not contain dependent sources today. And then on Wednesday's class meeting after our exam, we will talk about what to do when a dependent source is in the circuit. So let's start with Thevenin's theorem. So Thevenin's theorem states that any linear two-terminal electrical network can be replaced at the terminals with a voltage source VTH, which will stand for V Thevenin, in series with a resistance RTH. So effectively what Thevenin's theorem states is that we can make any linear two-terminal network look like a practical voltage source, because a practical voltage source contains a voltage source in series with a resistance. Now, in order to determine the Thevenin voltage, there are a special set of rules. And in order to determine the Thevenin resistance, there are a special set of rules. And so we'll talk about those now. So the Thevenin voltage VTH is defined as the open circuit voltage across the terminals of the live network, where a live network simply means that all of the independent voltage sources are actually, let me restate that, all of the independent sources, regardless whether they are voltage source or current source, are left on. So a live network literally means that it's been energized by something. Okay. The Thevenin resistance RTH is defined as the resistance seen by looking into the open circuited terminals of the dead network, where a dead network is one in which all of the independent sources have been turned off. And we turn off the independent sources to figure out Thevenin's resistance in the exact same way that we turned off independent sources when using the superposition technique. Walker. Seen. So let's unpack what this means by working an example. So this will be our network of interest. Let's just make this an 8-volt source. A 6-ohm resistor. Four-ohm resistor. That ohm sign looks funky. And a 2-amp current source, like so. And we want to find the Thevenin equivalent circuit seen by the 6-ohm resistor. So effectively, we are going to try to replace everything that isn't the 6-ohm resistor by a practical voltage source. Okay. So to find the Thevenin voltage, we redraw our circuit. Just be aware that I'm about to make you erase something, so you might want to hold on just a smidge. All right, so this is our original circuit. The Thevenin voltage is defined as the open circuit voltage across a set of terminals. Since we are finding our Thevenin equivalent resistance with respect to the 6-ohm resistor, we are going to take that resistor out of the circuit entirely. And the terminals where that 6-ohm resistor were connected are the open circuited terminals over which our Thevenin voltage is going to be found. I am choosing to find the Thevenin voltage with a positive polarity voltage on top. In your homeworks and on your exam and all that kind of stuff, which, just to be clear, this material is not on the exam on Monday. It will be the first topic on exam number 2. I will explicitly specify where the positive polarity terminal should be located for a Thevenin voltage. Okay, so I'm telling you here, we're doing it with positive polarity on top. In all of your subsequent problems, you will be told where to do it. In the grand scheme of things, it's really not going to matter particularly, but I like to give you guys a little bit of instruction here. So now we need to figure out how to find that Thevenin voltage VTH. Anybody have any thoughts? Well, we have a practical voltage source on the left-hand side, which we definitely could source transform into a practical current source. But would that actually help anything? I would argue that it wouldn't, because on the right-hand side, we have a current source in series with a resistor, and we can't transform our way out of that. So this is a single loop circuit now. So I would argue that KVL would be the appropriate method to use. But we can make a simple observation as well. Because this is a single loop circuit and there is a current source driving current around a fixed amount of current around this circuit, we know what all of our resistor voltage drops are, right? Just using Ohm's law, I could say very easily that this voltage is going to be 20 volts because 2 amps times 10 ohms is going to look like 20 volts. And I've defined the positive polarity terminal such that the current is flowing into the positive polarity terminal so that I don't have to get squirrely with Ohm's law. Okay. So we know how much current is flowing around the loop. Now, applying Kirchhoff's voltage law around the left-hand loop of this circuit, we would have VTH is going to wind up being equal to 20 volts plus 8 volts is 28 volts. Yes. All right, so this 2 amps of current is the only current flowing in this circuit. And so 2 amps times 10 ohms gives me 20 volts all day. And I have defined the positive polarity terminal such that the current was flowing into the positive polarity terminal so that I didn't have to use the Ohm's law with a negative sign in it. Okay. So for this particular problem, we wound up using a combination of Ohm's law and Kirchhoff's voltage law in order to find our open circuit voltage. What method we choose to use is going to change depending on the circuit that we are given. Any method can be used to find this open circuit voltage. So we could use nodal, mesh, whatever, for a more complex circuit. So it's just really going to be whatever you're comfortable with is what you should be using to find that open circuited voltage, okay? And we'll work another example here in a minute. So now that we know our Thevenin voltage, we can find our Thevenin resistance. So once again, I'm going to redraw my circuit, and then I'm going to erase some things. So starting with my original circuit, where I have my 8-volt source in series with my 10 ohm resistor. Here's a 6 ohm resistor. Here is a 4 ohm resistor. Here's a 2 amp current source. Because I'm finding my Thevenin equivalent circuit with respect to the 6 ohm resistor, the first thing I need to do is take the 6 ohm resistor out, which is going to leave behind the open circuited set of terminals that I'm looking into to find my equivalent resistance, okay? Now, in order to determine my Thevenin equivalent resistance, I need to be looking at a dead network. Emily, how do I turn off a voltage source? Somebody at Emily's table, help her out. I disagree. Short circuit. We turn off a voltage source by replacing it with a short circuit because the voltage drop across a short circuit is always 0, and we want to make sure that we have 0 volts, right? Because that's what an off voltage source means. So I'm going to replace my 8-volt source with a short circuit. I also need to turn off my current source. Emily, I'm going to pick on you again. How do I turn off current source? So with a voltage source, we replace it with a short circuit. For a current source, we should do kind of the opposite type thing. Open circuit, absolutely right. So we are going to eliminate our current or turn off our current source by replacing it with an open circuit. So this might look a little bit confusing. There are 2 open circuited set of terminals in our network now. We are finding the Thevenin equivalent resistance with respect to the 6 ohm resistor, which means we need to be looking into the terminals where the 6 ohm resistor was located. So what is our Thevenin equivalent resistance here? It's just 10. So the 4 ohm resistor is effectively just dangling, right? So if we called this terminal A and this terminal B, and we tried to find the equivalent resistance between terminals A and B, we would have, so here's A and here's B, right? So between A and B, we would have a 10 ohm resistor. And then between A and somewhere else that isn't connected to B, we will have a 4 ohm resistor. So our resistance between A and B is just 10 because the 4 from our perspective isn't part of a closed loop, right? So all we see is the 10 ohm resistor. So putting these two things together, our Thevenin equivalent circuit says that this circuit, where we have an 8-volt source in series with a 10 ohm resistor, 6 ohm resistor like so, 4 ohm resistor like so, 2 amp source like so, is electrically equivalent to a 28-volt source, which is just VTH, in series with a, 10 ohm resistor, my apologies, in series with my 6 ohm resistor. So effectively, I just connect my Thevenin equivalent circuit to the element that I was finding it with respect to. Okay. So this details how to find the Thevenin equivalent circuit with respect to a particular element. Okay. We can also find the Thevenin equivalent circuit with respect to a particular set of terminals. Whenever we're doing it with respect to a set of terminals, we already have an open circuited set of terminals, so we don't need to take anything out of the network, right? Only when we're finding the Thevenin equivalent circuit with respect to a particular element do we take that element out. And after we cover Norton equivalent circuits here in just a moment, then I'll work a problem where we are just given a set of terminals. So, any questions on the Thevenin equivalent circuit process? Okay. To form the Thevenin equivalent circuit, we need to find the open circuit voltage, which is the same as VTH. And we also need to find the Thevenin resistance, which is just the resistance looking into the terminals of a dead network. So if we found it with respect to a different resistor, I'd be willing to bet we'd get a different Thevenin equivalent voltage and a different Thevenin equivalent resistance. Can't really do it with respect to sources, but you can do it with respect to any passive element, so resistors, capacitors, and inductors. And when we get to our transient analysis discussion, which will be one of the last topics that we talk about before exam 2, in order to figure out what the time constant for a circuit is, we'll actually be taking the Thevenin equivalent resistance with respect to our energy storage element or elements. Protein.
The Thevenin equivalent circuit of another would all three of those circuits be equivalent? The original one will sound the we thought this equivalent circuit of.
So if we were to find the Thevenin equivalent circuit with respect to the 4 ohm resistor, would it be equivalent to the Thevenin equivalent circuit with respect to the 6 ohm resistor? I don't necessarily think so. When we're finding the Thevenin equivalent circuit with respect to the 6 ohm resistor, we're effectively making sure that the 6 ohm resistor absorbs the exact same amount of power, and we don't really care about anything else, right? We're ensuring that the voltage drop across that resistor stays the same, the current flowing through that resistor stays the same, and therefore the power absorbed by that resistor stays the same. So doing it with respect to the 4 ohm resistor or the 10 ohm resistor, we're definitely going to get a different Thevenin voltage and a different Thevenin resistance. So it's hard to say that the Thevenin equivalents with respect to different resistors are going to be equivalent to each other. Walker. Should be 28. That's just shitty penmanship on my part. Anything else? All right, so let's take a look at Norton's theorem. So Norton's theorem was developed about, I think it was 60 years after Thevenin's theorem. Okay. And Norton's theorem states that any linear two-terminal electrical network may be replaced at the terminals by a current source, I Norton, in parallel with a resistance R Norton. So Thevenin's theorem says that we can replace any two-terminal electrical network with a practical voltage source. Norton's theorem states that we can replace any two-terminal electrical network with a practical current source. Okay. The rules for finding the Norton current and the rules for finding the Norton resistance are what I'm about to give you. Okay. So the Norton current I Norton is defined as the short circuit current flowing through the terminals of the network and the Norton resistance of the live network, excuse me. And the Norton resistance is defined as the resistance seen looking into the open circuited terminals of the dead network. So oops, I didn't even write it correctly here. R Norton. So one thing that we can see is that the Norton resistance and the Thevenin resistance are defined in literally the exact same way. So they represent the exact same voltage. The process for finding the Norton resistance is identical to the process for finding the Thevenin resistance. In fact, after right now, I will never call it a Norton resistance again. I will only refer to it as a Thevenin resistance. The Norton current is distinctly different from the Thevenin voltage, though. The Thevenin voltage was defined as the open circuit voltage across the terminals. The Norton current is defined as the short circuit current across the terminals. So if we look at our example from earlier, where we have an 8-volt source connected to a 10 ohm resistor, connected to 6 ohm resistor. Here is our 4 ohm resistor. Here is our 2 amp source. If we want to find the Norton current with respect, and let me write this down. Find the Norton equivalent circuit with respect to the 6 ohm resistor. What we'll do is take our original circuit, and instead of replacing this 6 ohm resistor with an open circuited set of terminals, we're going to replace it with a short circuit. And our Norton current is defined as the current flowing through that short. So how could we find this current? Killing. Yes, we could do this with mesh, but it's, oh my God, I hate that so much. We could do this with mesh. However, I believe that there is a significantly easier way. Kirchhoff's current law. Oh yeah, that basic fundamental law of circuit analysis. All right. So I would argue that this current flowing in plus this current flowing in add together to make I Norton. Does anybody have a problem with that? So what's the current flowing through the 10 ohm resistor? 8 volts over 10 ohms. What's the current flowing in through the 4 ohm resistor? So that looks like 2.8 amps. No need for a system of equations whatsoever. Stop using mesh as a crutch. He says knowing no one will listen. Yes, it absolutely will work, but it's complete and utter overkill for this. I'm an electrical engineer telling you not to do it. Yeah, no, I know. I can rant and moan about you guys using nodal and mesh for everything. It's going to change nothing. But truly, understanding the fundamentals will help you in the later parts of this class much more than being able to throw nodal and mesh at everything. Because you're not going to be able to solve a system of equations that contains complex numbers using your calculator. Using your computer, you can do it all day long, but that's not going to help you on your test. So not understanding how to apply the fundamental rules like KCL and KVL to a circuit is going to bite you in the ass when you get to the later parts of this class. And for those of you that are electrical engineering majors, which is about a third of you, it's really going to bite you in the ass when we get into our transistor circuits and all of that kind of good stuff, where they're all just going to be ugly and nasty. And it's going to be, because they're nonlinear, require us to rely on those fundamental laws. Okay. All right. So we don't need to find the Norton equivalent resistance because we already found the Thevenin equivalent resistance for the circuit, and they're literally the exact same things. So our Norton equivalent circuit is simply the 2.8 amp source in parallel with that 10 ohms of resistance, which was our Thevenin resistance. And then that is connected across the terminals of our 6 ohm resistor. So that's our Norton equivalent circuit. Over here to the right is our Thevenin equivalent circuit. So I'm just going to redraw that really quickly. So both of these circuits are electrically equivalent to our original circuit, which means they're electrically equivalent to each other. So hopefully surprising absolutely no one, the Thevenin equivalent circuit is the source transformation of the Norton equivalent circuit and vice versa. Yes. What changes if I do that? Have I defined any voltages or currents or anything? Yeah, doesn't matter at all. Yeah. All right, so fundamentally then, we know that the Thevenin voltage is equal to the Norton current times the Thevenin resistance. We know that the Norton current is equal to the Thevenin voltage divided by the Thevenin resistance. And because I'm running out of room, I'll just put this one over here. We also know that the Thevenin resistance can be described as the ratio of the Thevenin voltage to the Norton current, which means we inherently have a way to check our answers here if we know how to solve for all three quantities. Or if we want to be lazy, we can solve for two and use the relationships to find out what the third one is. Okay. All right. So let's work another example. This time finding the Thevenin equivalent circuit. Hojun. Repeat the question, please. So we found the Norton current, 2.8 amps. We found the Norton resistance previously because the Norton resistance is defined as the same in the exact same way as the Thevenin resistance. So once I know those two pieces of information, I know what my Norton equivalent circuit is going to look like because Norton's theorem tells me that the Norton equivalent circuit is a current source in parallel with a resistor. Just like here, I found the Thevenin equivalent voltage, the Thevenin equivalent resistance, and put them together to get the Thevenin equivalent circuit. Because all I need to find for a Thevenin equivalent circuit is a voltage source and a resistance. So Thevenin's theorem, just to rehash things here, states that I can replace any two-terminal electrical network with a practical voltage source. Norton's theorem states that I can replace any two-terminal electrical network with a practical current source. All right. Absolutely, yes. So this is what Thevenin and Norton equivalent circuits are mainly used for. Particularly is you would actually measure them at different points in your circuit and then use it to determine whether or not you're going to burn out resistors and things like that, because you're going to exceed their tolerance when you connect things to them, right? So you can take any large, ugly network, measure the open circuit voltage, measure the dead network resistance, and then just treat it as a practical source to do your power analysis without having to understand everything that's going on in the circuit. That's absolutely how it is applied in practice. We can also technically use it to simplify circuits, because if you can isolate a portion of a big ugly circuit into a two-terminal network, you can then find the Thevenin or Norton equivalent of that part of the circuit, plug it back in, and hopefully you've made the circuit smaller or easier to analyze. You very much could use this, particularly on the last two problems that are specifically about finding the resistance that gives you where maximum power transfer occurs, to do this instead of doing source transformations. Absolutely, you could. You're not going to explicitly be tested on this until exam 2, but you can apply it wherever you feel like. Okay. All right, so let's say that we have the following network. Let's put an 8-volt source here. Four ohm resistor here. 10 ohm resistor here. Um, 6 ohm resistor here. 5 ohm resistor here. A 3-volt source here. And this will be our open circuited set of terminals. Let's call these A and B. And our goal is to find VTH. Let me explicitly say plus on top, I Norton, direction down, and RTH with respect to terminals A and B. So which quantity do you guys care to solve for first? What the heck is happening? Just a moment here. I have an extra HDMI cable. I don't think it's that. I think it's literally the gravity of the cable hanging off the way that this thing is installed under the table makes it gradually fall out of the socket. Not, yeah. Put the HDMI thing vertically on the top of the table would be my best guess. There are several design things about this building that don't make sense to me, like why all of the plugs are on the floor where people can accidentally kick the plugs and shear the pins off, which if you unplug one of these, you'll notice that there's a ground pin stuck inside one of the receptacles, and I have informed the building manager about it, I think 4 times at this point, and nothing ever gets done. So when somebody gets shocked, that's their problem, not mine. All right, what do we want to find first? Thevenin equivalent voltage, Thevenin equivalent circuit, or excuse me, current, gosh, resistance, or Norton equivalent current. Cameron, you're looking at me, tell me one of 3. Resistance, okay. So we're gonna find RTH first. So find our Thevenin equivalent resistance. What do we need to do? Turn off our voltage sources. We turn them off by short circuiting them, okay? So that's the short circuit. That's a short circuit, all right? Now we need to find the equivalent resistance looking in between terminals A and B. I can't look at this thing directly and figure out what's going on, so I'm going to identify my nodes and do that kind of business. So here's one node. Here's another node. Here's a third node. Here's A. Here's B. So directly between A and B, I have a 5 ohm resistor, right? Because A is blue and B is green. I can also go from A to C to B. So let's put C here. So I can go from A to C through the 6 ohm resistor. And then, oh, and I'm calling C this red node. And then I can go from C to B through either the 4 ohm resistor or the 10 ohm resistor. Sorry, I put 40 instead of 4. So before we move along with this, is this representation correct? I don't personally see anything wrong with it, but you know. So just to be clear, between A and B, we have the 5. Between A and C, we have the 6. And then between C and B, we have the 4 and the 10. So that checks out to me. So let's see, 4 in parallel with 10 is 40 over 14. Plus 6. And then that is going to be times 5 divided by answer plus 5. I get 310 over 97 ohms. Yep, 310 over 97. Anybody else get that result? Good deal. All right. So we found our Thevenin equivalent resistance. Now let's find either our Thevenin equivalent voltage or our Norton equivalent current. Brandon, tell me which of those two we're going to do. Voltage, all right. So to find my Thevenin equivalent voltage, what am I looking for? The open circuit voltage across terminals A and B. And we were specifically told to find that with a positive polarity terminal on top. So that means we are looking for this voltage. How are we going to find that voltage? Nope, because we're finding the Thevenin equivalent voltage, which means we need to be looking at a live network. So there are 6 different paths that I can think of to do KVL for this equation. I don't know any of the currents, and every path that I can think of has at least one resistor in it, so that might not, KVL by itself probably isn't enough. Nodal is easier. Yes. So let's talk very briefly about why nodal would be easier in this case, right? So how many nodes do we have in this circuit? 5 nodes. That sounds very daunting considering that there are only 2 meshes, right? That being said, if I were to choose my ground node to be on bottom, exactly right. So 3 of those 5 nodes now have a known voltage. The bottom one would be 0. The top left node would have a voltage of 8 volts. And the middlemost node would have a voltage of 3 volts, which means I only have 2 unknown voltages left in my circuit. So I have a 2 equation, 2 unknown system using nodal, or a 2 equation, 2 unknown system using mesh. Since we're trying to find a voltage, nodal gives us voltages, so we don't have to do any additional post-processing to our results like we would have to do with mesh. So I would argue that nodal is the better choice for this particular circuit. So choosing the bottom node as ground and calling this node VA and this node here, actually that's not the right one. Let's call this one BC. I'm intentionally skipping over B because logically we would call this one node B and it's already at ground. Okay. So if we tried to set up our Kirchhoff's current law equations here, KCL at node A is going to give us VA minus 3 volts over 5 ohms plus VA minus VC over 6 ohms is equal to 0. So just to be clear here, that's this current plus this current leaving node A. Now I'm going to apply KCL at node C. So I'm going to have this current, and this current. So that's going to look like VC minus 8 volts over 4 ohms plus VC minus 3 volts over 10 ohms plus VC minus VA over 6 ohms is equal to 0. And now I can solve that system. Right? So solving it as a 2 equation, 2 unknown system, my coefficient for VA in my first equation is 1/5 plus 1/6. My coefficient for VC in my first equation is negative 1/6. My constant term is going to be 3 volts over 5 ohms, so I'm just going to put that as 3 over 5. In my second equation, my coefficient for VA is negative 1/6. My coefficient for VC is 1/4 plus 1/10 plus 1/6. And my constant term is going to be 8 over 4 plus 3 over 10. In solving this, I get VA is equal to 416 over 97. And VC is equal to 566 over 97. So now that I've solved for those nodal voltages, what's V Thevenin? VA. Why is it just VA? Because the positive polarity terminal of our Thevenin voltage is at node A. The negative polarity terminal of our Thevenin voltage is at ground. So VA represents the exact same thing as our Thevenin voltage. All right. So lastly, let's find I Norton. The moment you've all been waiting for. Mesh is actually the best way to do this. We're going to use that to check to make sure that we did everything else right. Yeah. So looks like I have 3 meshes to deal with. Let's call this A, B, and C. I don't have any current sources, so I'm just going to do KVL at A, B, and C and call it a day. So KVL at A, we're going to have negative 8 volts plus 4 ohms times I1 plus 10 ohms, excuse me, times IA, excuse me. 10 ohms times IA minus IB plus 3 volts will be equal to 0. Then I have KVL at mesh B. So that's going to look like 10 ohms times IB minus IA plus 6 ohms times IB plus 5 ohms times IB minus IC is equal to 0. And lastly, KVL at mesh C is going to look like negative 3 volts plus 5 ohms times IC minus IB is equal to 0. And I'm going to solve this system as a 3x3 system. So my coefficient for IA is going to look like 4 plus 10. In my first equation, my coefficient for IB is going to look like negative 10. I don't have any IC, and then I'm going to have 8 minus 3 for my constant term. In my second equation, my coefficient for IA is negative 10. My coefficient for IB is 10 plus 6 plus 5. My coefficient for IC is negative 5. My constant term is 0. And in my last equation, my coefficient for IA is 0. My coefficient for IB is negative 5. My coefficient for IC is positive 5. And my constant term is positive 3. Solving this, I get IA is equal to 55 over 62. IB is 23 over 31. IC is 208 over 155. So what's I Norton? Just IC. So the $1 million question is, did we do all of this analysis correctly? So is V Thevenin divided by I Norton equal to R Thevenin? Well, V Thevenin was 416 over 97. I Norton was 208 over 155. So 416 over 97, 155 over 208. We get 310 over 97 volts per amp is an ohm. which I believe is exactly the answer we got when we determined the Thevenin equivalent resistance directly. Yes, ma'am. If we had defined our Norton current in the opposite direction or our Thevenin voltage with the opposite polarity, we would have had to have thrown in a negative 5. So we're looking at it from a perspective of absorbed power for electrical equivalency, which means we want the current flowing into the positive polarity terminal. Yep. Yes, sir. You could. I just wanted to show you that you could use, if you can find all three, you can check your one. But yeah, technically speaking, you only need 2 of the quantities to find the third one. So, like on your exam or something like that, like I might ask you for the Thevenin equivalent voltage and the Norton equivalent current. And if you can find one of those and the resistance, you can find the answer to the other one, kind of thing, without having to do any real circuit analysis, if you so chose. All right, any other questions regarding, yes, ma'am? So not only are they supernodes, they're supernodes that contain ground, right? So formally, what we should have done, let's call this VD and VE. We should have had voltage relationship equations for this super duper node where VD was equal to 8 volts and VE was equal to 3 volts. But because hopefully we're comfortable enough with it now, we realize we don't actually need to go through that rigmarole. And we could have just substituted those voltages in directly, which is exactly what I did. Yeah, but technically speaking, we do have 2 supernodes here. Because of the place we chose ground, we don't have to write a KCL equation at either that node D or that node E, because those supernodes contain ground. Yep, absolutely. So if, for example, there had been a resistor right here, I couldn't have done what I did, because now my 8 volts would have been between this node and whatever this node was labeled. So I couldn't have written this equation right here as it is. Yes. Any other questions? All right, work on the in-class assignment. On Monday, we don't officially have class because the exam is in the evening, but I will be here for a review session. Okay. That being said, here's how my review sessions work. You come in with questions to ask of me. I answer them. As soon as you run out of questions, I leave.